Determining constants via equating coefficients. Okay, so we've talked about why we do partial fraction decomposition, breaking down complex rational expressions into simpler ones, and we've already figured out how to set up the general form of that decomposition. Now, this slide focuses on the next crucial part, actually finding the values for those unknowns we introduced. Think back to when we wrote out our partial fraction decomposition. We ended up with expressions like a over x minus a plus b over x minus b, and so on. A, b, c, these are the constants we need to determine. They aren't just letters, they represent specific numbers. This slide tells us that there are several ways to solve for these constants, but we're going to focus on one particularly powerful and reliable method, the method of equating coefficients. It's a systematic, purely algebraic approach. What that means is, we'll be manipulating equations, not guessing and checking. And the really good thing about this method is that it works no matter what kind of factors you have in the denominator, whether they're simple terms like x minus a, repeated factors like x minus a squared, or even more complicated, irreducible quadratic factors like x squared plus 1. It's a universal method, and that's why we're going to spend time mastering it. In the next few slides, we'll break down exactly how this method works, step by step. We'll start with the underlying principle, which is based on the idea of an identity, and then we'll walk through a complete example. So, let's move on to understanding what an identity actually is. Conceptual overview. Okay, so let's move on to slide 2, where we'll build the core understanding behind how equating coefficients actually works. The fundamental idea here is based on something called an identity. Now, what exactly is an equation? Well, an identity is simply an equation that is true for every possible value you could plug in for the variable, in this case, x. It's not just true for some values of x, it's universally true. Think of it this way: if you have two polynomials, and remember, a polynomial is an expression with terms like x raised to different powers. If those two polynomials are identical, meaning they are the same polynomial just written perhaps in a slightly different way, then their corresponding coefficients must be equal. Let me illustrate with an example. Suppose we have the polynomial a x squared plus bx plus c, and it's equal to another polynomial x squared plus ex plus f. If these two polynomials are identical, that means a must equal b must equal e, and c must equal f. It's a direct, one-to-one correspondence between the coefficients of the same powers of x, so, if you have an x squared term on both sides, the number multiplying x squared must be the same on both sides. The same applies to the x terms and the constant terms. Now, why is this important for our partial fraction decomposition? Well, after we set up our decomposition and clear the denominators, which we'll see in the next slides, we'll end up with an equation that looks like this. Because of this identity principle, we can equate the coefficients of the corresponding powers of x on both sides of the equation. This gives us a system of linear equations that we can then solve to find the unknown constants, a, b, c, and so on, that we need for our decomposition. This is the key to the whole method, so make sure you understand this concept of an identity. Step-by-step procedure. Okay, so we've talked about why equating coefficients works. Because of the idea of an identity, where polynomials are truly equal for all values of x now, let's break down how to actually do it, step by step. This slide outlines the procedure, and it's really quite systematic. First, step 1, set up the decomposition identity. This is where you simply write out the equation that represents your partial fraction decomposition. Remember, we've already figured out what form the decomposition will take. We're just writing it down now. So, if you start with a proper rational function, which will represent as p of x divided by q of x, you write it equal to the sum of your partial fractions. As shown in the example, if you have two linear factors in the denominator, it might look like a divided by x minus a plus b divided by x minus b. Just make sure this matches the form you determined earlier. Next, step 2, clear the denominators. This is a crucial algebraic step. To get rid of those pesky fractions, we multiply both sides of the equation by the original denominator. Q of x, this will cancel out the denominators on the left side, leaving you with a regular polynomial equation. In our example, this transforms the equation to P of x equals a times the quantity x minus b, plus b times the quantity x minus a. Now, step 3, expand and group terms. This is where we simplify the right-hand side. Distribute the a and b into the brackets. Then, the key is to group together terms with the same power of x, so collect all the x terms, all the constant terms, and so on. In the example, after expanding and grouping, we get P of x equals the quantity a plus b times x, plus the quantity negative a times b minus b times a. Moving on to step 4. Equate the coefficients. This is the heart of the method. Now that we have a polynomial on each side of the equation, we can compare the coefficients of corresponding powers of x. Remember, the coefficient is the number multiplying a particular power of x, so the coefficient of x to the power of n on the left-hand side must equal the coefficient of x to the power of n on the right-hand side. This applies to the constant term as well. The constant term on the left must equal the constant term on the right. This comparison will give you a system of equations. Finally, step 5. Solve the system of equations. You now have a set of linear equations with unknowns a, b, c, and so on. You can solve this system using methods you've likely learned before, like substitution or elimination. The solutions you find will be the values of your constants, completing the partial fraction decomposition. Keep in mind, as we move forward to the example on the next slide, this is a very reliable method, especially when dealing with more complicated denominators. It's a bit more work up front, but it avoids the pitfalls of the substitution method we briefly mentioned. Illustrative example. Here's our problem. We need to find the constants a and b for the decomposition of the function x plus 5, all divided by the product of x minus 1 and x plus 2. Step 1. Set up the identity. Remember, we've already established the form of the partial fraction decomposition. Now we write out the equation. So, we have x plus 5 divided by x minus 1 times x plus 2, and this is equal to a divided by x minus 1 plus b divided by x plus 2. This is simply restating what we know from the decomposition process. Step 2. Clear the denominators. To get rid of those pesky fractions, we multiply both sides of the equation by the common denominator, which is x minus 1 times x plus 2. This gives us, on the left side, just x plus 5. On the right side, the x minus 1 and x plus 2 terms cancel out, leaving us with a times x plus 2 plus b times x minus 1. Step 3. Expand and group terms. Now, let's expand the right-hand side. A times x plus 2 becomes x plus 2a, and b times x minus 1 becomes bx minus b, so our equation now looks like this. X plus 5 equals x plus 2a plus bx minus b. Next, we group like terms. We collect all the terms with x together and all the constant terms together. This gives us x plus 5 equals a plus b times x plus 2a minus b. Step 4. Equate the coefficients. This is the heart of the method. We compare the coefficients of corresponding powers of x on both sides of the equation. On the left-hand side, we have 1 times x, so the coefficient of x is 1. On the right-hand side, the coefficient of x is a plus b. Therefore, we can write our first equation. 1 equals a plus b, we'll call this equation 1. Now, let's look at the constant terms. On the left-hand side, we have the constant 5. On the right-hand side, the constant term is 2a minus b. So, our second equation is 5 equals 2a minus b, we'll call this equation 2. Step 5. Solve the system of equations. We now have a system of 2 linear equations with 2 unknowns, a and b. There are several ways to solve this. Here, we'll use the elimination method. Notice that if we add equation 1 and equation 2, the b terms will cancel out. So, a plus b plus 2a minus b equals 1 plus 5. This simplifies to 3a equals 6. Dividing both sides by 3, we find that it equals 2. Now that we know a, we can substitute it back into either equation 1 or equation 2 to solve for b. Let's use equation 1. 2 plus b equals 1. Subtracting 2 from both sides, we get b equals negative 1. Final result. Therefore, the decomposed form of our original function is 2 divided by x minus 1 divided by x plus 2. Okay, let's work through a concrete example to solidify our understanding of the equating coefficients method. As we discussed on the previous slides, this method is powerful because it works reliably for all types of partial fraction decompositions. And there you have it. We've successfully determined the constants a and b using the equating coefficients method. Remember, this method is a systematic approach that will work for more complex problems as well, especially those involving repeated or irreducible quadratic factors, which we'll explore further. As we move forward, keep in mind the workflow we discussed. Clear denominators, expand, group, equate, and solve. Real-world analogy. Think of equating coefficients like a financial audit. Now imagine a company preparing its financial statements. Their total assets, everything the company owns, are categorized, let's say into cash, property, and stocks. On the other side, they have total liabilities, everything the company owes, also categorized into cash, property, and stocks. The audit is only considered successful, and the books are considered balanced if the amount in each specific category matches exactly. So, the total cash assets must equal the total cash liabilities, the total property assets must equal the total property liabilities, and so on. You absolutely cannot balance a cash asset with a property liability. That wouldn't make any sense, right? You must match cash with cash and property with property. Everything needs to correspond correctly. Similarly, in algebra, when we equate coefficients, we're doing something very similar. Remember, we're breaking down our original rational function into simpler fractions with unknown constants. When we set up our equation and clear the denominators, we're essentially saying that the left-hand side and the right-hand side are identical polynomials. Just like in the audit, this means we can only match corresponding terms. We can only match the coefficient of x with the coefficient of x, the constant term with the constant term, the coefficient of x squared with the coefficient of x squared, and so on. This is the core principle behind the method. Okay, let's move on to a real-world analogy to help solidify your understanding of equating coefficients. This slide aims to make the abstract concept more concrete. This analogy should help you visualize why we need to equate the coefficients of corresponding powers of x. It's all about ensuring that both sides of the equation are perfectly balanced, category by category, just like a balanced financial statement. Now, let's move on to the next slide, where we'll discuss some common mistakes to avoid when applying this method. Being aware of these pitfalls will help you avoid frustration and ensure you get the correct answer. Common mistakes to avoid. Okay, so we've learned how to determine constants in partial fraction decomposition by equating coefficients. Now, let's look at some common pitfalls students often encounter. This slide will help you avoid those mistakes and ensure you get the correct answer consistently. 1. Sign errors during expansion. This is extremely common. When you're multiplying out terms with negative signs, it's easy to make a mistake. For example, if you have negative b multiplied by the quantity x minus 1, remember to distribute that negative sign correctly. So, negative b times x minus 1 becomes negative bx plus b. Don't just write negative b times x as negative bx and then forget about the negative b times negative 1. Pay close attention to those signs. A small error here can throw off your entire solution. 2. Incorrect grouping. After you've cleared the denominators and expanded everything, you must group like terms together. This means collecting all the terms with the same power of x, so all the terms with x to the power of 1, all the terms with x to the power of 0, which are just the constant terms, and so on. If you miss a term or put it in the wrong group, your system of equations will be incorrect, and you won't be able to solve for a, b, and c properly. 3. Confusing coefficients with variables. This is a conceptual error. Remember, we're not solving for x. X is just a placeholder. We are solving for the unknown constants, a, b, c, and so on. These are the values we need to find. The variable x is simply a tool that allows us to create an identity, an equation that's true for all values of x. Keep your focus on isolating those constants. 4. Ignoring the zero coefficient. This is a subtle but important point. Sometimes, a certain power of x might not appear on the left-hand side of your equation. For instance, there might be no x squared term. If that happens, it means the coefficient of x squared on the left-hand side is 0. You must remember to include this when you equate coefficients on both sides. So, if there's no x squared term on the left, you need to set the coefficient of x squared on the right-hand side equal to 0 as well. This ensures your system of equations is complete and accurate. Alright, so keep these common mistakes in mind as you practice. Now, let's move on to the final slide, where we'll summarize the key takeaways from this entire method. Key takeaways. First point, identity principle. Remember, the entire method hinges on the idea of an identity. An identity is an equation that's true no matter what value you substitute for x. So, if we have two polynomials that are identical, meaning they are equal for all values of x, then each corresponding power of x within those polynomials must have the same coefficient. For example, if we have a polynomial like a x squared plus bx plus c, and it's identical to x and ex plus f, then a must equaled b must equal e, and c must equal f. This is the core logic that allows us to create our system of equations. Next, linear systems. What we're essentially doing is taking a problem involving rational functions, fractions with polynomials, and transforming it into something we're already good at solving, a system of linear equations. By clearing denominators, expanding, and grouping terms, we create equations where our unknowns, like a, b, and c, are related linearly. This makes it solvable using techniques like substitution or elimination, which you've likely practiced before. Now, universality. This is a really important point. You might be thinking, couldn't I just pick convenient values for x and plug them in to solve for a and b? That's the substitution method, and it can work in some cases. However, equating coefficients is far more reliable. It always works, even when you have repeated factors in the denominator, like xa squared or irreducible quadratic factors, things you can't easily factor further. The substitution method can get tricky with those, but equating coefficients remains a solid approach. Finally, let's look at the workflow. This is a handy reminder of the steps we've been following. First, clear denominators, multiply both sides of the equation by the common denominator to get rid of the fractions. Then, expand, distribute any terms, and simplify. Next, group, collect all the terms with the same power of x together. After that, equate, compare the coefficients of corresponding powers of x on both sides of the equation. And finally, solve. Use your favorite method to solve the resulting system of linear equations for the unknown constants. Okay, let's recap everything we've learned about determining constants using the method of equating coefficients. This is our final slide, and it's all about solidifying the key takeaways. So, there you have it. Equating coefficients is a powerful and reliable technique for determining the constants in partial fraction decomposition. Remember these key takeaways, and you'll be well equipped to tackle these types of problems.